a mysterious space visitor has recently passed its closest approach to Earth, flying by at a distance of 64 million miles. That's close in cosmic terms, close enough that professional telescopes can see it clearly, close enough that dedicated amateur astronomers with the right equipment can track it across the sky, close enough that we can study its properties in detail and ask questions about where it came from and what it represents. And those questions are urgent, because this object, this new arrival in our solar system, appeared at a moment that cannot be coincidence, at a time when another mysterious visitor called 3I Atlas has been capturing global attention and triggering debates about whether we're witnessing natural phenomena or something far stranger. This new object might be something totally natural, born on the outskirts of the solar system in the vast frozen realm called the Oort Cloud, where comets sleep for billions of years before gravitational disturbances send them falling inward toward the sun. That's the conventional explanation, the safe interpretation that requires no extraordinary assumptions. Or, and this is where things become uncomfortable for conventional astronomy, some unknown civilization could be examining us from above right at this moment, sending probes into the inner solar system, studying our planets and our emerging technological civilization, observing with instruments and intentions we can only guess at. This new object looks a lot like another strange wanderer called 3I Atlas, and you'll understand why we say strange pretty soon if you're not already familiar with it, because 3I Atlas has been exhibiting behaviours that challenge conventional explanations, that strain natural frameworks, that have led serious researchers to at least consider the possibility of artificial origin, even if most remain sceptical. The similarities between these two objects, the timing of their appearances, the questions they both raise, all of it creates a pattern that demands attention even if we don't yet know what that pattern means. So could both of them come from the same place outside our solar system? Could they be related, part of a coordinated reconnaissance, multiple probes from the same mission arriving at different times along different trajectories but with common purpose? Or is the timing pure coincidence? Two unrelated objects from different origins happening to pass through during the same period by random chance that seems improbable but isn't impossible. We don't know yet. We can't know without more data, without tracking both objects carefully, without analysing their compositions and trajectories and behaviours to look for connections that might reveal common origin or definitively rule it out. What we do know is that this new object is relatively close to us, in space terms of course, and scientists are now studying it closely with every available instrument. They first spotted it inside our solar system, and people are paying attention because it showed up not long after 3I Atlas passed near our Sun. The timing is striking. 3I Atlas reached perihelion, its closest point to the Sun, in late October 2024. This new object was discovered just days later, on November 2nd, 2025. That's barely a year later. And while a year might seem like a long time in human terms, in astronomical terms it's essentially simultaneous. Two objects appearing in a rapid succession when interstellar visitors or even Oort Cloud comets are typically separated by years or decades. On November 2nd, 2025, astronomer Gennady Borisov, the same person who discovered interstellar comet 2I, Borisov, in 2019, found this new object. That name should be familiar if you've been following interstellar object discoveries. Borisov has a proven track record. His 2019 discovery of 2I Borisov was the second confirmed interstellar object ever detected after Oumuamua in 2017. Both of those discoveries changed astronomy, proved that objects from other star systems pass through ours regularly, established that we can detect and study them if we're watching carefully. And now Borisov has found another unusual object, one that might or might not be interstellar, but that definitely deserves the careful attention that his previous discoveries have taught us to apply. This new object has got its official designation now. It's listed in NASA's database and in the Minor Planet Center's catalogues as C2025 V1. That designation tells us several things. The seal prefix indicates it's a comet, an object showing activity, outgassing, producing a coma and possibly a tail as ices sublimate under solar heating. The 2025 tells us the year of discovery. The V1 is a sequential designation indicating it was the first such object discovered in late October 2025, during the second half of the month when discoveries get the V letter code. Simple cataloguing, routine astronomical nomenclature, but behind that dry designation is an object that's anything but routine. C2025V1 has some unusual features that immediately caught researchers' attention and raised questions about its origin and nature. Its orbit is tilted at 113 degrees relative to the ecliptic, the plane in which Earth and most other planets orbit the Sun. That's a massive tilt. Most solar system objects have orbital inclinations measured in single digits, or at most a few tens of degrees. They orbit roughly in the same plane because they formed from a rotating disk of material around the young Sun, and that rotational momentum kept things mostly flat. But 113 degrees means C2025V1 is moving almost perpendicular to the planetary plane, coming up from below or diving down from above, crossing through the solar system at an angle that looks nothing like the orderly arrangement of planets and asteroids and typical comets. That extreme inclination immediately suggests distant origin. Objects from the Oort Cloud, that vast spherical shell of icy bodies surrounding the solar system at distances of thousands of AU, can have any inclination because the Oort Cloud is spherical rather than flat. Gravitational perturbations from passing stars or from the galactic tide can nudge Oort Cloud objects into the inner solar system from any direction, producing comets that approach from above, below, or at steep angles. So a 113-degree inclination is consistent with Oort Cloud origin, but it's also consistent with interstellar origin. An object coming from another star system, entering ours from arbitrary direction, could have any inclination depending on the relative motion between the solar system and its origin point. Even more bizarre, and this is where connections to 3i Atlas start becoming intriguing, C2025V1's orbital plane is almost at a right angle to the path of 3i Atlas. Their orbital planes are nearly perpendicular. If you imagine 3i Atlas travelling through the solar system on one tilted plane, and C2025V1 approaching on a plane rotated 90 degrees from that, you get the geometry. This perpendicular relationship is unusual. If both objects came from the same source, if they were ejected from the same stellar system, or released from the same mission, you'd expect their orbital planes to be similar, aligned, or at least not perpendicular. The perpendicularity suggests different origins, independent arrivals, no direct connection. But geometry can be deceiving. Without more analysis, without modelling how orbits evolve over long timescales, under various perturbations, we can't rule out that perpendicular planes at arrival might result from initially similar trajectories that got twisted by planetary encounters or by the object's own propulsion if they have any. Plus, C2025V1 doesn't have a clear comet tail, which is odd for an object designated as a comet, as something showing enough activity to warrant the C classification. Comets are defined by their tails, those spectacular structures of dust and gas streaming away from the nucleus under pressure from solar radiation and solar wind. When you see photos of famous comets like Hale-Bopp or Mach-Naught, the tails are the dominant visual feature, extending millions of kilometres, creating those iconic images that capture public imagination. But Susskind 2025V1, despite being active enough to show coma, despite outgassing sufficient to produce the diffuse envelope around the nucleus, apparently doesn't have a prominent tail. That could mean several things. One possibility is viewing geometry. Tails point away from the Sun, always, regardless of the comet's direction of motion. If we're viewing C2025V1 from an angle, where the tail points directly toward or away from us, edge on so to speak, it would be much less visible than if we were seeing it from the side. Projection effects matter enormously in astronomy. The same object can look dramatically different depending on viewing angle, so the lack of obvious tail might just be bad geometry from our perspective. As the object moves, as Earth's position changes, the viewing angle will shift and a tail might become visible. Another possibility is that the outgassing is weak, producing insufficient material to form a visible tail, even though there's enough activity to create coma. Not all comets are equally active. Some produce spectacular displays with huge tails. Others putter along with minimal emission, barely visible even when close to the Sun. The activity level depends on composition, on what ices are present and how volatile they are, on the surface properties of the nucleus, on whether there's exposed ice or an insulating dust mantle covering it. C2025 V1 might just be a quiet comet, active but not dramatically so. Or, and this is the interpretation that connects to questions about 3I Atlas and artificial hypotheses, the lack of tail might indicate that what we're seeing isn't natural outgassing at all, but controlled emission from thrusters or vents on an artificial object. Rocket exhaust doesn't form long tails the way cometary sublimation does. It's more collimated, more directional, dissipating quickly rather than streaming away for millions of kilometers. If C2025 V1 were under propulsion, if it were making trajectory adjustments using onboard systems, we might see coma from the exhaust but not extended tails. That's speculative, certainly, but it's consistent with observations and can't be dismissed without evidence. Right now, C2025 V1's orbit has an eccentricity of 1.0095. And let me break that down in human language because orbital eccentricity is technical but important for understanding what this number tells us about the object's origin. Eccentricity measures how elliptical or circular an orbit is. A perfect circle has eccentricity of 0. Ellipses have eccentricities between 0 and 1, with higher numbers meaning more elongated ellipses. Parabolic orbits, objects that are barely bound to the Sun with exactly the escape velocity, have eccentricity of exactly 1. And hyperbolic orbits, trajectories that carry objects completely out of the solar system never to return, have eccentricities greater than 1. So C2025 V1's eccentricity of 1.095 is just barely above 1. It's hyperbolic, technically, meaning the object is on a trajectory that will carry it out of the solar system eventually. But it's only barely hyperbolic. If that number was well above 1, if the eccentricity was 1.1 or 1.5 or 2.0, it would mean the object definitely came from outside the solar system, arriving with significant excess velocity that could only come from interstellar space. But because it's only just a bit above 1, only 0.95 above the parabolic threshold, the most likely explanation is that C2025 V1 came from the Oort Cloud. That's a giant faraway shell of icy objects that surrounds the solar system, extending from perhaps 2,000 AU out to 100,000 AU or more, halfway to the nearest stars. The Oort Cloud is thought to contain billions or even trillions of cometary nuclei, frozen leftovers from solar system formation that got scattered to enormous distances by gravitational interactions with the giant planets billions of years ago. These objects orbit the Sun but barely. Their orbital velocities are tiny, their binding energies minimal. Small perturbations from passing stars, from the galactic tide, from giant molecular clouds, any of these can nudge an Oort Cloud object slightly, giving it just enough velocity to fall inward toward the Sun. When an Oort Cloud comet falls inward from those enormous distances, it arrives with velocity very close to parabolic. It's falling from essentially infinite distance, accelerating under solar gravity, and by the time it reaches the inner solar system, its velocity is almost exactly escape velocity. Almost, but usually not quite. Depending on exactly where in the Oort Cloud it started and what perturbation sent it inward, it might arrive with velocity slightly below or slightly above escape velocity. Slightly below gives eccentricity slightly less than 1. Slightly above gives eccentricity slightly greater than 1, like C2025 V1's 1.0095. Now, scientists check this interpretation by basically rewinding the object's path, integrating the orbit backwards in time, sending it all the way back to about 1000 AU. That's 1000 times farther than the Earth is from the Sun, well beyond the realm where planetary perturbations matter significantly. At that huge distance, the planets can't mess with its motion anymore. You're far enough out that the Sun dominates gravitational influence almost exclusively. When astronomers redo the orbit calculation from that point, when they take the observed trajectory and extrapolate it backwards to 1000 AU accounting only for solar gravity, the eccentricity usually drops below 1. The object's original orbit before it encountered the planets was slightly elliptical rather than hyperbolic. That confirms Oort Cloud origin. The object was orbiting the Sun barely and got perturbed inward by some external influence. But here's where it gets tricky. At the same time, even a tiny gravitational push from Jupiter, while passing by, could make even a normal Oort Cloud comet look like it has an eccentricity slightly above 1. Jupiter is massive. Its gravity well is deep. When a comet passes within a few AU of Jupiter, the gravitational interaction can add or subtract velocity, can bend the trajectory significantly. If a comet arrives from the Oort Cloud with eccentricity just below 1, barely bound, and then gets a slight gravity assist from Jupiter on the way in, that boost could push the eccentricity above 1, making the object appear hyperbolic even though it's actually solar system origin. And on top of that, small blasts of gas coming off the comet's surface can also change the numbers a little. This is called non-gravitational force, the rocket effect, where outgassing from the nucleus acts like tiny thrusters, pushing the comet in directions determined by where the active vents are located and how the nucleus is rotating. These forces are small but measurable. Over months of observation, they accumulate, changing the orbit enough that calculated eccentricity can shift by small amounts. If you observe a comet and calculate eccentricity without accounting for non-gravitational forces, you might get a number slightly higher than the true gravitational orbit would suggest. So to put it simply, C2025 V1's eccentricity of 1.0095 probably isn't indicating true interstellar origin. It just looks that way because of small pushes from planets and gas bursts from outgassing. When astronomers do the full analysis, accounting for planetary perturbations and non-gravitational forces, the original orbit before it entered the planetary region probably had eccentricity below 1, confirming that this is an Oort Cloud comet rather than an interstellar visitor. That's the consensus interpretation. That's what most researchers studying this object believe. But consensus isn't certainty. The analysis depends on models of how planets perturb orbits and how outgassing produces non-gravitational forces. Those models work well for typical comets, where we have lots of data and experience. But C2025 V1 isn't typical. Its extreme orbital inclination, its unusual activity pattern, its timing relative to 3I Atlas, all of these make it an outlier, and for outliers, models based on typical cases might not apply perfectly. There could be subtleties we're missing, effects we haven't accounted for. Until the full orbital analysis is published, until experts have examined it carefully and built confidence that Oort Cloud origin is correct, we should maintain some epistemic humility about the certainty of that conclusion. C2025 V1 is still exciting, even if it comes from the Oort Cloud, even if it's not interstellar, because studying it gives us a chance to analyze material from that distant region and learn how our solar system formed and evolved. The Oort Cloud is a fossil record. Those objects out there are pristine samples from the earliest days of the solar system, frozen in time, preserved in deep freeze for 4.6 billion years. When we study Oort Cloud comets, when we analyze their composition through spectroscopy and measure their properties through observation, we're learning about the conditions and materials present when the Sun and planets formed. That's invaluable scientific data regardless of whether the object is interstellar. But the question of whether C2025 V1 is related to 3I Atlas, whether they share common origin, that question becomes harder to answer if C2025 V1 is from the Oort Cloud rather than interstellar space. If both objects were interstellar, if both came from beyond the solar system, then common origin is plausible. They could be from the same stellar system, ejected by the same planetary dynamics, travelling through the galaxy on similar trajectories that happen to intersect our solar system within a year of each other. Or they could be artificial, probes from the same mission, deployed at intervals, arriving on different paths designed to provide comprehensive coverage of the inner solar system. But if C2025 V1 is from the Oort Cloud, native to our solar system, then it can't share origin with 3I Atlas, unless 3I Atlas is also from the Oort Cloud rather than interstellar. And that contradicts the clear evidence from 3I Atlas's trajectory. 3I Atlas has eccentricity well above 1, approaching 2, indicating definite interstellar origin with significant excess velocity. Its composition shows isotopic ratios different from solar system materials, confirming it formed elsewhere. So if 3I Atlas is interstellar, and C2025 V1 is Oort Cloud, they're not from the same source. They're not related except by coincidental timing. Unless, and this is where speculation ventures into territory that most astronomers would dismiss, but that we should at least consider given the stakes, 3I Atlas deployed C2025 V1. If 3I Atlas is a probe that released smaller subprobes during its passage through the inner solar system, if C2025 V1 is one of those deployed objects now on its own trajectory, then they could be related despite different apparent origins. The deployed probe would inherit the mothership's velocity initially, but could use its own propulsion to modify its trajectory to enter an orbit that looks Oort Cloud-like, even though it actually originated from the interstellar visitor. That would explain the timing, the appearance within a year of 3I Atlas's perihelion passage, while accounting for the different orbital parameters. This scenario sounds like science fiction. It requires accepting that 3I Atlas is artificial and capable of deploying subprobes, both extraordinary claims. But it's logically consistent with observations. It provides a framework that explains the coincidental timing without invoking random chance, and it makes testable predictions. If C2025 V1 is a deployed probe, it should show signs of active propulsion, trajectory changes that can't be explained by natural outgassing. Its composition might differ from typical comets, might show anomalies similar to what's been reported for 3I Atlas, and there might be other deployed objects, additional discoveries waiting to be made as more surveys scan the sky looking for unusual movers. Now let's get back to the mystery of 3I Atlas itself, because understanding what makes 3I Atlas strange is essential for evaluating whether C2025 V1 could be related to it. Before anything else, let's explain what 3I Atlas actually is, at least what we know about it from observations. It's most likely a comet, basically a huge dirty snowball flying through space, composed primarily of water ice mixed with other frozen volatiles like carbon dioxide and methane and ammonia, all embedded in a matrix of dust and rocky particles and organic compounds. You can't see it with your own eyes or with a regular telescope, at least not easily. At its brightest it reaches about magnitude 9, which requires binoculars or a small telescope under good conditions. It's not a naked eye object like the great comets of history. But there's good news for anyone wanting to observe it. A powerful telescope in Italy, the Virtual Telescope project run by astrophysicist Gianluca Massi, has been streaming 3I Atlas live for free. Anyone with internet access can watch this mysterious object as it passes by, seeing real-time images captured by professional equipment and explained by expert commentary. That kind of public access to cutting-edge astronomy is remarkable, democratizing observation that would have been restricted to professional astronomers just decades ago. Scientists think this comet weighs about 33 billion tons based on estimates of its size and assumed density. That number is hard to imagine, so here are a few comparisons to make it more concrete. The Eiffel Tower weighs around 10,000 tons, iron and steel construction totaling that mass, so 33 billion tons is the same as a whopping 3.3 million Eiffel Towers. Imagine millions of those iconic structures stacked together, and you get a sense of the mass we're talking about. And if you decide to compare the space visitor to buildings, 33 billion tons is about the same as the weight of several huge city areas made entirely of steel and concrete, skyscrapers and infrastructure and roads all combined. But even all that size isn't the wildest part. The truly remarkable thing about 3I Atlas isn't its mass, but its behaviour, the way it moves and the things it does that don't quite fit natural explanations. Some experts think this object might be a piece of unknown technology from outside our galaxy. And they're not saying this just for fun, not proposing the idea as clickbait or attention-seeking. There are real reasons behind the theory, genuine anomalies in the observations that make the artificial hypothesis at least worth considering, even if it remains unlikely. 3I Atlas was first noticed in July 2024 by NASA's Asteroid Terrestrial Impact Last Alert System, or ATLAS. That's a network of telescopes specifically designed to detect near-Earth objects, asteroids and comets that might pose impact hazards. The system scans the sky repeatedly, comparing images taken on different nights, looking for objects that move against the background stars. When ATLAS detected 3I Atlas, the motion was immediately obvious. This wasn't a near-Earth asteroid on a typical elliptical orbit. This was something moving fast on a trajectory that looked hyperbolic, that suggested origin from beyond the solar system. Shortly after initial detection, NASA confirmed that the object wasn't from our solar system at all. It's an interstellar object, only the third ever discovered with confirmed interstellar origin. The first was Oumuamua in 2017, that strange elongated object that tumbled through the inner solar system without showing any cometary activity despite close approach to the Sun. Oumuamua looked long and flat, possibly cigar-shaped or pancake-shaped depending on interpretation, and it didn't behave like a normal rock, showing non-gravitational acceleration that required explanation. The second interstellar visitor was Comet 2I Borisov in 2019, discovered by Gennady Borisov, the same astronomer who found C2025 V1. Borisov looked like a normal comet, showed expected outgassing and tail development, fit comfortable within conventional frameworks even though it was interstellar. Now we have 3I Atlas, and it is enormous compared with the other two. Its nucleus is estimated at up to 6 kilometers wide based on brightness and assumed albedo. That's substantially larger than Oumuamua, which was only about 400 meters long at most, and much larger than 2I Borisov, which had a nucleus around 1 kilometer across. The size difference matters because it affects everything else about the object, from how much outgassing it can sustain to how visible it is, to how much thermal inertia it has, affecting temperature response to solar heating. Besides being huge, 3I Atlas is unusual in several other ways that have captured scientific attention and generated the speculation about possible artificial origin. As it moves through the solar system, it's releasing massive amounts of carbon dioxide and gas, production rates measured through spectroscopy that show emission far exceeding what typical comets produce at similar distances from the Sun. This suggests that 3I Atlas is 3 to 5 orders of magnitude, which means 1,000 to 100,000 times more massive than the other two known interstellar visitors, or that it's far more active than size alone would predict, outgassing at rates that require explanation beyond simple solar heating of surface ices. Such an enormous difference is a real scientific mystery. Why would one interstellar object be so much more massive or active than others? Is it compositional? Does 3I Atlas contain more volatile ices that sublimate readily? Is it structural? Does the nucleus have a porous rubble pile structure that allows heat to penetrate deeply and drive out gassing from internal reservoirs? Or is it something else, some mechanism beyond natural cometary processes that produces the observed emission rates? These questions don't have definitive answers yet, and that uncertainty creates space for alternative interpretations, including the possibility that the massive outgassing isn't natural sublimation at all, but exhaust from active propulsion systems, modifying the trajectory according to mission requirements that we can only speculate about, but which observations increasingly suggest might be operating. It's also travelling incredibly fast, about 150,000 km/h, which is almost 200 times the speed of sound on Earth. Now, that velocity might not sound extraordinary for an interstellar object, because anything coming from another star system has to be travelling fast enough to overcome the Sun's gravity and escape the solar system. Typical interstellar velocities relative to the Sun are in the range of 20 to 40 kilometers per second, which translates to roughly 45,000 to 90,000 rls. So 3I Atlas at 150,000 rls, about 67 kilometers per second, is on the high end but not impossibly so. Oumuamua was travelling at similar speeds. Fast-moving stars in the galaxy can impart high velocities to objects they eject. But what makes this velocity interesting isn't the absolute number, it's how that velocity changes, how the trajectory evolves in ways that don't match purely gravitational predictions. Unlike objects in our solar system, which followed curved elliptical paths determined entirely by gravity, moving predictably according to Kepler's laws and Newton's equations, 3I Atlas is moving on what appears to be a nearly straight line through the inner solar system. At the scales and distances involved, hyperbolic trajectories do look relatively straight compared to the tight ellipses of planets and asteroids. An interstellar visitor is just passing through, barely deflected by solar gravity, approaching from one direction and departing in nearly the opposite direction along paths that are almost linear at large scales. But when you measure carefully, when you track position precisely over weeks and months, you can detect the curvature, the bending of the trajectory by solar gravity. And that's where 3I Atlas becomes anomalous. The observed trajectory doesn't quite match the predictions. There are residuals, differences between where the object should be based on gravitational calculations and where it actually is. Those residuals indicate non-gravitational forces, accelerations beyond what the Sun and planets can produce, and the magnitude and direction of those forces, the way they correlate with solar distance and viewing geometry, suggests something more than just random outgassing from a rotating nucleus. That alone makes 3I Atlas stand out from typical comets, and even from other interstellar visitors. But there's more. These odd behaviours, the size and the activity level, and the trajectory anomalies, have led some researchers to consider a pretty unexpected idea. 3i Atlas might be a probe sent by another civilization, possibly to study Earth, or the inner solar system more broadly. According to this theory, the object could be a sign of some kind of intelligence from beyond our solar system, technology deployed for reconnaissance or scientific observation, or purposes we can't even guess at because the motivations of an unknown civilization are fundamentally unknowable. Why do they think this? Well, because the object's movement doesn't match what you'd expect from something controlled only by gravity and natural outgassing forces. The trajectory precision, the way it's approaching Jupiter's hill radius with accuracy that seems too good to be coincidental, suggests navigation rather than ballistic motion. Natural comets don't target specific locations. They follow paths determined by initial conditions and gravitational interactions, paths that are chaotic and unpredictable over long timescales. But 3i Atlas's trajectory looks designed, optimized, like someone calculated where they wanted to go and executed burns to achieve that destination. It also passes close to Venus, Mars, and Jupiter, and these are the planets that might be especially interesting for an outside civilization to observe. Venus represents extreme greenhouse conditions, a cautionary example of planetary climate gone wrong. Mars shows evidence of past habitability, ancient river valleys and lake beds suggesting water once flowed on the surface. And Jupiter is the giant that dominates the outer solar system, the planet whose gravity shapes asteroid orbits and protects the inner system from excessive comet bombardment. If you were designing a probe to study our solar system, if you wanted to gather data on planetary diversity and conditions, these are exactly the worlds you'd prioritize. The close approaches aren't impacts or even particularly close by astronomical standards. 3i Atlas isn't buzzing these planets at minimum distance, but its trajectory brings it within observing range of all three during different phases of its passage, providing optimal viewing geometry for extended observation if the object contains sensors designed to collect such data. That could be coincidence. With only 8 planets and a hyperbolic trajectory that has to pass through the inner system to reach perihelion, some planetary encounters are inevitable. But the specific combination, the way the trajectory samples different planetary environments, looks suspicious to anyone inclined to see pattern rather than randomness. Another very unusual feature of 3i Atlas's path is that its orbit is tilted only a little compared to the plane of the solar system, about 5 degrees. Most interstellar objects should have random inclinations because they're coming from arbitrary directions in the galaxy. There's no preferred orientation. You'd expect a distribution where some objects have low inclinations, others have high inclinations, and a few come in nearly perpendicular or even retrograde. But 3i Atlas has low inclination, moving nearly in the ecliptic plane, the same plane where planets orbit. And it moves in the opposite direction to most planets, retrograde motion, which is common for comets and not in itself unusual. But combined with the low inclination, this creates specific viewing geometry. An object in retrograde orbit with low inclination spends more time visible from Earth than one with high inclination. It crosses the sky at angles that make tracking easier. It's accessible to telescopes for longer periods. This feature might allow the object, or its creators if it's artificial, to take extremely precise measurements of planets, things like their orbits and sizes, to plan a perfect flight route through the solar system, or to gather scientific data with optimal observational coverage. Whether this geometry is intentional design or fortunate coincidence depends on your prior probability assessment for artificial origin. If you think alien probes are vanishingly unlikely, then the geometry is just lucky chance, one of those things that happens sometimes in a large enough sample of objects. But if you're open to the possibility that advanced civilizations send probes to other stellar systems, if you think such reconnaissance is plausible, then the geometry looks like evidence of deliberate planning, like someone chose this trajectory specifically because it provides the coverage and viewing angles they wanted. And if 3i Atlas suddenly changes direction at some point, if future observations show trajectory modifications that can't be explained by outgassing, that could mean it's using a built-in engine instead of simply drifting through space on a ballistic path. We haven't seen unambiguous evidence of this yet. The trajectory anomalies detected so far are subtle, explainable at least arguably through non-gravitational forces from asymmetric outgassing. But the monitoring continues. Every position measurement, every astrometric observation contributes to refining the orbital solution. And if that solution starts showing changes that exceed what natural processes can produce, if the object makes a maneuver, the artificial hypothesis gains credibility dramatically. Now, new photos have also shown that 3i Atlas has at least 7 jets blasting material into space, some shooting in totally opposite directions. This is visible in high-resolution images from Hubble and from ground-based telescopes during optimal viewing conditions. The jets aren't uniform. They don't create a simple symmetric coma. Instead, there are discrete features, directional emissions, structures that suggest localized sources on the nuclear surface rather than global sublimation. 7 distinct jets have been identified, possibly more that are fainter or oriented such that we can't see them clearly. And here's what's striking: some of these jets point in opposite directions. You have emission toward the Sun and emission away from the Sun. You have jets pointing perpendicular to the Sun direction, emissions that can't be explained by simple, solar heating driving sublimation from the Sunward hemisphere. This geometry is unusual but not impossible for natural comets. Comet nuclei rotate, often with complex tumbling motions. Active vents can be located anywhere on the surface. Depending on the rotation state and the vent positions, you can get jets pointing in various directions that, from Earth's viewing angle, appear to be simultaneous, even though they might activate at different times during the rotation cycle. But explaining the specific geometry observed 7 jets with some in opposing directions requires specific assumptions about nucleus shape and rotation and vent locations. You need a model that fits the observations. And while such models can be constructed, while there's nothing physically impossible about the required conditions, the fact that you need rather specific geometry to make it work means the configuration isn't generic. It's special. It requires explanation. And that creates opportunity for alternative interpretations. If 3i Atlas is artificial, if those jets are thruster plumes rather than natural outgassing, then having jets in opposing directions makes perfect sense. That's exactly how you'd design a propulsion system for 3-axis attitude control and trajectory modification. You need thrust in multiple directions to rotate the spacecraft, to point it in desired orientations, to execute burns along different axes. Chemical rockets or ion engines mounted at various locations on the surface, firing in coordinated patterns, would produce exactly what we're observing. Multiple discrete jets, some in opposing directions, creating forces that sum to the net acceleration needed for navigation. Now, if this thing is just a normal comet, if the jets really are natural sublimation from solar heating, it would have had to lose a huge amount of its original mass when it passed near the Sun, way more than just 10 to 20%. The reason is that outgassing produces relatively weak thrust. The velocities of sublimating molecules are measured in hundreds of meters per second, thermal velocities determined by temperature. To produce significant trajectory changes using only that low exhaust velocity, you need to eject enormous amounts of mass. The rocket equation is unforgiving. Low exhaust velocity means low efficiency, which means high propellant consumption for a given delta V. Only some of that ejected material would actually push the object in one direction. The rest gets emitted in other directions from other vents, contributing to the coma but not to net thrust. So the total amount blown off would need to be massive, potentially 50% or more of the nucleus mass, to produce the trajectory anomalies observed. If that's what happened, then there should be now a giant cloud of gas and dust around 3i Atlas. All that ejected material doesn't disappear. It spreads out, creating an extended coma and tail, dissipating gradually over weeks and months as solar radiation pressure and solar wind push it away. And if that cloud exists, if there really is that much material in the coma, it'll be pretty easy to figure out what the comet is made of. Spectroscopy can identify molecules by their emission lines. The brightness of those lines indicates abundance. By measuring the spectrum carefully, by identifying which molecules are present and in what quantities, researchers can infer the composition of the nucleus ice that's sublimating to produce the coma. That's standard cometry science, techniques that have been refined over decades of observation. The James Webb Space Telescope will check this when 3i Atlas gets closest to Earth on December 19, 2025. JWST has infrared capabilities that are ideal for detecting molecules like water, carbon dioxide, methane, all the species expected in comets. It can measure composition with precision that exceeds what ground-based telescopes achieve, and crucially, JWST can detect faint extended emission, can characterize the coma structure in ways that reveal how much material has been ejected and what it's made of. If the composition analysis shows that 3I Atlas contains typical cometary ices in expected ratios that supports natural origin, but if the composition is anomalous, if there are unexpected molecules or missing species or isotopic ratios that don't match solar system materials, that raises more questions. But if 3I Atlas is not a normal comet and is actually some kind of technology, it wouldn't need to lose that much material to modify its trajectory. Engines built by an advanced civilization could give it a boost while using way less gas because they shoot it out way faster. Faster exhaust gives more push with less fuel. That's the fundamental principle of rocket propulsion, captured in the Tsiolkovsky rocket equation. Exhaust velocity appears in the exponent. Increasing it even modestly produces dramatic improvements in efficiency. Chemical rockets achieve exhaust velocities around 3 to 5 kilometers per second. Ion engines can reach 30 to 50 kilometers per second. More exotic propulsion concepts, nuclear thermal or nuclear electric systems, could go higher still. A technological object wouldn't need to blast away big chunks of itself the way a natural comet would to achieve the same delta V. It could make substantial trajectory changes while ejecting relatively modest amounts of propellant, amounts that would produce visible jets, but not the enormous diffuse coma that natural sublimation of 50% of the nucleus would create. So the absence of a massive coma, the fact that 3I Atlas shows discrete jets rather than huge diffuse emission, could be evidence favouring artificial propulsion over natural outgassing. Of course, this argument cuts both ways. Defenders of natural origin can point out that we don't know how much mass 3I Atlas actually lost, that our estimates of coma density might be underestimating the total ejected material, that viewing geometry could hide extended faint emission that would be obvious from a different angle. Without direct mass measurements before and after perihelion, without comprehensive models of the coma that account for all possible viewing effects, we can't definitively say whether the observed coma is too small for natural origin, but we can say it's consistent with artificial propulsion, that the technology hypothesis provides a framework that fits observations without requiring special pleading about unusual geometries or compositions. So to sum it up, there's still a big mystery around 3I Atlas. The object exhibits multiple anomalies: size, activity level, trajectory precision, jet geometry, timing of variations in brightness and emission. Each anomaly individually might have natural explanations, but collectively, they create a pattern that some researchers find difficult to reconcile with purely natural processes, and that's where the artificial hypothesis gains traction, not because any single observation proves technology, but because the ensemble of observations fits better with design than with chance. Could it really be a technological mothership that released small probes into the inner solar system? That's the question underlying speculation about connections to C2025 V1 and potentially other undiscovered objects. If 3I Atlas is a probe or a carrier vehicle, if it has the capability to deploy smaller subprobes, then its passage through the inner solar system might have involved multiple deployment events. The object approaches. At calculated moments along its trajectory, it releases probes. Those probes use their own propulsion to maneuver into desired orbits, perhaps targeting specific planets or establishing observation posts at strategic locations. The mothership continues on its trajectory, completing its own mission, while the deployed probes operate independently. This scenario has precedent in human space exploration. We've done exactly this with missions like Galileo, which released a probe into Jupiter's atmosphere while the orbiter continued its mission, or Cassini, which deployed the Huygens probe to Titan's surface while the main spacecraft remained in Saturn orbit. Separation of functions, using a carrier vehicle to deliver specialized payloads, is efficient engineering. An advanced civilization might use the same approach at interstellar scales. But C2025 V1 doesn't fit that idea cleanly, unless one of the objects used some kind of engine to dramatically change its trajectory after deployment. The closest their orbits ever come is about 46 million miles. That's the minimum distance between their orbital paths in three-dimensional space, and the two objects themselves, the actual bodies, were never closer to each other than about 140 million miles, even at the point of nearest approach in their respective orbits. Those are huge separations, far too large for any plausible deployment scenario. If 3I Atlas had released C2025 V1, the separation would have been minimal initially. A few hundred meters, maybe a few kilometers if the deployment involved a spring-loaded ejection or a small impulse, but certainly not millions of miles. To go from close proximity to 140 million mile separation in the year between 3I Atlas perihelion and C2025 V1 discovery would require massive delta velocity changes of kilometers per second sustained over long periods. That's far beyond what the tiny non-gravitational acceleration detected in 3I Atlas could provide. The tiny non-gravitational push detected in 3I Atlas, measured at about 10^8 AU per day squared in some analyses, is nowhere near strong enough to close this gap or to have created it if the objects started together. That acceleration, integrated over a year, produces velocity changes measured in meters per second, not kilometers per second. It's enough to fine-tune a trajectory, to make small adjustments that accumulate into meaningful course corrections over months. But it's not enough to separate two objects by 140 million miles in 1 year, unless they had very different initial velocities, which brings us back to the problem that deployment scenarios should produce similar initial velocities. So C2025 V1 is almost certainly not one of the many probes people imagine 3I Atlas might have released, at least not based on simple deployment mechanics. The orbital geometries don't work. The separations are too large. The relative velocities required are implausible. If there's a connection between these objects, it's not direct deployment at some point along 3I Atlas's trajectory. It would have to be something more subtle, some scenario we haven't thought of yet, some mechanism that explains the coincidental timing and the unusual properties both objects share without requiring direct physical association. One possibility is that both objects, 3I Atlas and C2025 V1, were deployed much earlier by something else, some carrier vehicle that passed through the outer solar system or even through the Oort Cloud years or decades ago. That carrier could have released multiple probes on different trajectories, timed to arrive at the inner solar system at roughly the same period. 3I Atlas approaches on one trajectory with high eccentricity, clearly interstellar. C2025 V1 approaches on a different trajectory with barely hyperbolic eccentricity, looking Oort Cloud-like. Both arrive within a year of each other. Both show unusual properties, but there's no direct connection because they've been separated for years, following independent paths that were calculated during deployment to provide coordinated coverage. This scenario explains the timing without requiring impossible separations. It explains why the orbital geometries are so different, why C2025 V1 looks Oort Cloud native even if it's not. And it provides a framework for expecting additional discoveries, other probes from the same deployment that might be detected in coming months or years as surveys continue scanning the sky for unusual objects. But it also requires accepting even more extraordinary claims than the hypothesis that 3I Atlas alone is artificial. Now we're proposing not just one alien probe, but multiple probes, and a carrier vehicle, and a mission architecture of substantial sophistication. The layers of assumption multiply. Another possibility, and this is more conservative, is that C2025 V1 is exactly what it appears to be, an Oort Cloud comet perturbed inward by random gravitational influences, and its timing relative to 3I Atlas is pure coincidence. Oort Cloud comets arrive regularly. Several are discovered each year. Most are faint and unremarkable. Occasionally one becomes bright enough to see with the naked eye and captures public attention. But dozens of fainter ones pass through unnoticed except by dedicated surveys. C2025 V1 could be one of these routine discoveries that happened to occur during a period when attention was already focused on interstellar objects because of 3I Atlas. The unusual orbital inclination, the lack of prominent tail, these could be random variations within the normal range of cometary diversity, rather than indicators of anything anomalous. Not all comets look alike. They form under different conditions, have different compositions, exhibit different behaviours. C2025 V1 might just be an outlier, unusual but natural, drawing attention because of context rather than intrinsic strangeness. If it had been discovered at a different time, if 3I Atlas wasn't in the news, it might have been catalogued and studied and forgotten without generating speculation about artificial origin or connections to other objects. But context matters. The fact is that C2025 V1 was discovered when it was, during a period of heightened awareness about interstellar visitors and unusual solar system objects. That context shapes interpretation. It makes people look more carefully at data, ask more questions, consider alternatives they might otherwise dismiss. And that heightened scrutiny, even if it leads ultimately to conventional explanations, has value. It ensures that if there are genuine anomalies, if C2025 V1 or 3I Atlas or future discoveries really do represent something beyond natural processes, we'll notice. We won't miss the signal because we weren't looking carefully enough. There's also the question of what future observations might reveal. Both objects are still being tracked. C2025 V1 is being observed with increasing cadence as more telescopes target it, building up the orbital solution, measuring photometry to look for brightness variations that might indicate rotation or outbursts, collecting spectra to characterize composition. If those observations show anything anomalous, if the orbit evolves in unexpected ways, or the composition is bizarre, or the activity pattern doesn't match cometry models, that will strengthen arguments for artificial origin, or at least for unusualness that demands explanation beyond standard frameworks. Similarly, with 3I Atlas, the December 19th closest approach to Earth provides optimal observing conditions. JWST observations, Hubble follow-up, ground-based spectroscopy, all of it will provide data that either confirms natural cometry behavior or reveals additional anomalies. The X-ray detection from XRISM established that 3I Atlas is the first interstellar object ever detected in X-rays, a distinction that's either compositionally interesting or potentially significant for artificial hypotheses, depending on whether follow-up confirms the emission mechanism as pure charge exchange or suggests additional energy sources. And then there's the Jupiter encounter in early 2025. If 3I Atlas enters orbit at Jupiter's Hill radius, if it demonstrates trajectory control sufficient to achieve stable capture rather than passing through, that would be extraordinary evidence favouring artificial origin. Natural comets don't do that. The probabilities are infinitesimal. Capture requires precise velocity and position at encounter, conditions achievable through deliberate navigation, but vanishingly unlikely through random chance. So the Jupiter encounter is a test, potentially the definitive test if the object does something that unambiguously requires propulsion. All of this brings us to the broader question of how we should think about unusual objects in our solar system. The discovery of Oumuamua changed the conversation. Before 2017, interstellar objects were theoretical, predicted by models but never observed. After Oumuamua, they became real, confirmed visitors from other stellar systems passing through ours in ways we could detect if we watched carefully. That paradigm shift, that transition from might exist to definitely exist, opened intellectual space for asking bigger questions about what else might be out there. And one of those questions is whether some interstellar visitors might be artificial. Before Oumuamua, suggesting that any astronomical object could be artificial technology was career-ending for professional astronomers. The idea was relegated to fringe speculation, not serious science. But Oumuamua's anomalies, particularly its non-gravitational acceleration without visible outgassing, created legitimate scientific debate about explanations. Natural hypotheses were proposed: nitrogen ice, hydrogen icebergs, dust-covered comets, but none fit perfectly. And that imperfect fit created space for Avi Loeb and others to argue that artificial origin deserved consideration, that light sail probes or other technology might explain observations better than contrived natural scenarios. The reception was hostile. Most astronomers criticized Loeb harshly, argued he was being irresponsible, claimed the artificial hypothesis was unscientific. But the debate happened. Papers were published arguing for and against various interpretations. The question got aired in professional journals and conferences, not just popular media. And that represents progress, a loosening of the taboo that previously prevented even mentioning artificial possibilities. Now with 3I Atlas showing its own suite of anomalies, the conversation continues with less resistance, more openness to examining evidence rather than reflexively dismissing unconventional ideas and that intellectual evolution, that willingness to ask strange questions and follow data even when it leads to uncomfortable places. That's what science is supposed to be about fundamentally. And that brings us to the practical question of what happens next. What observations are planned? What data might resolve the uncertainties that currently surround both C2025 V1 and 3I Atlas? Because we're not stuck with speculation forever. These objects are observable. They're accessible to our instruments. We can measure their properties, track their trajectories, analyze their compositions. And those measurements, accumulated over weeks and months, will either support natural explanations or reveal anomalies so profound that alternative frameworks become necessary. For C2025 V1, the immediate priority is refining the orbital solution. Every position measurement contributes to understanding the trajectory more precisely. The current eccentricity of 1.095 is based on preliminary orbit calculations using early observations. As more data accumulates, as the baseline of observations extends from days to weeks to months, the orbit calculation becomes more accurate. Uncertainties shrink, systematic errors average out, and crucially, we can measure whether the orbit is changing in ways that indicate non-gravitational forces. If C2025 V1 is a normal Oort Cloud comet, its orbit should remain stable except for small perturbations from outgassing that follow predictable patterns based on solar distance. Approaching the Sun, activity increases, outgassing accelerates, non-gravitational forces become measurable, but should correlate with brightness changes and gas production rates. Receding from the Sun, activity declines, forces diminish, the object settles onto a trajectory determined primarily by gravity, and the momentum changes accumulated during the active period. But if C2025 V1 is under active control, if it's making deliberate trajectory adjustments using onboard propulsion, the orbit evolution would look different. You'd see velocity changes that don't correlate with solar distance or activity level. You'd detect accelerations in directions that don't align with visible emission features. You'd observe maneuvers, sudden changes in trajectory that natural processes can't explain. These signatures would be unambiguous. They wouldn't require interpreting subtle anomalies or arguing about whether effects are large enough to exceed natural variation. Active propulsion produces clear signals that stand out from natural backgrounds. So the orbital monitoring continues. Professional observatories are allocated time to observe C2025 V1 at regular intervals. Amateur astronomers with capable equipment contribute observations, building a distributed network that provides temporal coverage no single facility can match. All of this data flows into orbit determination programs, sophisticated software that fits observations to gravitational models and solves for the parameters that best match measured positions. And if those fits start showing residual, systematic deviations that grow over time rather than averaging out, that's when things get interesting. Spectroscopic observation is equally important. Knowing what C2025 V1 is made of constrains models of where it came from and what it represents. If the composition matches typical Oort Cloud comets, if water ice dominates with smaller amounts of CO, CO2, methane, ammonia, all in ratios consistent with low temperature condensation in the outer solar system, that supports conventional origin. The object is what it appears to be, a frozen relic from the solar system's formation perturbed inward by gravitational influences. But if the composition is anomalous, if there are molecules that shouldn't be present, or if expected species are missing, or if isotopic ratios don't match solar system values, that raises questions. Where did this material form? Under what conditions? What processes created the observed composition? Natural explanations might still work, but would require invoking unusual formation environments or evolutionary processes that aren't well understood, and each additional layer of special pleading, each requirement for non-standard conditions, makes alternative explanations relatively more attractive. One specific thing to watch for is deuterium to hydrogen ratio. Deuterium, heavy hydrogen with an extra neutron, forms in specific proportions depending on temperature and chemical environment. The DH ratio in water ice is a sensitive indicator of formation conditions. Solar system comets show DH ratios about 2 to 3 times higher than Earth's oceans, reflecting formation in the cold outer regions where deuterium enrichment is efficient. But different stellar environments, different protoplanetary disk conditions produce different ratios. If C2025 V1 shows DH ratios significantly different from solar system norms, that would indicate formation elsewhere, in a stellar system with different chemistry or temperature history. That wouldn't prove artificial origin, but it would confirm exotic origin, would establish that even if the object is natural, it's not from the Oort Cloud, making the barely hyperbolic eccentricity a real indicator of interstellar origin, rather than an artifact of planetary perturbations. And if it's interstellar, the connection to 3I Atlas becomes plausible again. 2 interstellar visitors arriving within a year, that's either remarkable coincidence or meaningful pattern. Photometric monitoring, measuring how brightness changes over time, can reveal rotation state. Most asteroids and comets rotate, tumbling through space with periods ranging from hours to days. As they rotate, different surface features come into view. If there are bright and dark regions, if the shape is elongated rather than spherical, we see periodic brightness variations that encode information about rotation period and axis orientation. For C2025 V1, detecting such variations would help constrain physical properties and could reveal whether the object is behaving naturally or anomalously. Natural rotation is chaotic on long timescales. Comets outgas asymmetrically, creating torques that change rotation state unpredictably. But over the short term, over weeks of observation, rotation should be steady and periodic. You might see brightness varying with a consistent period, rising and falling as the object spins. Artificial objects, spacecraft with attitude control might show different patterns. Controlled rotation, deliberate orientation changes, maintenance of specific pointing directions, all of these would create photometric signatures distinct from natural tumbling. And then there's the question of activity evolution. How does C2025 V1's brightness and coma change as it moves through its orbit? Natural comets follow predictable activity curves. Approaching the Sun, they brighten as warming drives increasing sublimation. After perihelion, they fade as they recede and cooling reduces outgassing. The light curve has characteristic shape determined by the comet's heliocentric distance history and the response of surface ices to solar heating. C2025 V1's perihelion, its closest approach to the Sun, occurred recently. The object is now receding, moving outward, cooling down. Activity should be declining. Brightness should be dropping along a curve that follows inverse square law, with distance plus some additional fading as sublimation rates decrease. If observations show this expected pattern, that supports natural origin. But if activity doesn't decline as predicted, if the object maintains brightness, or shows irregular variations that don't correlate with solar distance, that's anomalous. That suggests energy sources beyond solar heating or controlled emission, rather than passive sublimation. For 3I Atlas, which is further along in its trajectory and has been observed more extensively, the critical observations are happening right now as it approaches closest distance to Earth. December 19th, 2025 represents the optimal viewing window. At minimum separation, roughly 140 million kilometers, every photon counts. Telescopes can collect maximum signal. Spectroscopy works at peak efficiency. Imaging reveals finest detail. This is the moment when we learn the most, when observations can detect features invisible when the object was more distant or will be invisible when it recedes beyond effective range. The James Webb Space Telescope observations scheduled for this period will be particularly revealing. JWST's infrared capabilities allow detection of molecules that don't emit strongly, invisible wavelengths: water, carbon dioxide, methane. These species have characteristic infrared signatures. Measuring their abundances precisely, mapping their distribution in the coma, tracking how emission varies with time and position, all of this provides constraints on what's happening at the nucleus and what processes are driving the observed activity. If JWST detects normal cometary composition in expected ratios, if the infrared spectrum looks like a standard comet's just scaled up to account for 3I Atlas's larger size, that would argue for natural origin despite the trajectory oddities. Maybe the orbit precision is coincidence. Maybe the jets are unusual geometry but still natural. Composition matching solar system materials would be difficult to reconcile with interstellar formation unless we invoke very specific scenarios where other stellar systems produce identical chemistry to ours. But if JWST detects anomalies, if there are unexpected molecules or missing species or abundance ratios that don't match any cometary model, that strengthens the case for something unusual. Not necessarily artificial, but at least not typical, and combined with the trajectory precision and the jet geometry and all the other oddities, compositional anomalies would create a cumulative case that becomes increasingly difficult to explain through natural processes alone. The X-ray observations are also continuing. XRISM's detection of X-ray emission from 3I Atlas was the first ever for an interstellar object. Chandra has now observed as well, though results haven't been publicly released yet. When they are, when we have independent confirmation of the X-ray emission, and more detailed spectroscopy showing which elements are producing the signal, we'll understand better whether this is just efficient charge exchange or whether there are additional energy sources contributing to the observed photons. if multiple X-ray observations all converge on a mission explained entirely by solar wind charge exchange with high ionization states, matching what models predict for the coma composition, that's consistent with natural origin. Charge exchange is well understood. It should produce X-rays from any active comet if solar wind conditions and coma density are right. 3I Atlas being the first detected just means it's the brightest or most favourable geometry, not that it's fundamentally different. But if the X-ray emission shows features that charge exchange can't explain, if there are energies or intensities or temporal variations that require additional mechanisms, that opens questions about what those mechanisms might be. Internal heat sources, particle acceleration processes, something generating high-energy photons through pathways beyond standard cometry physics. Each alternative needs detailed modelling to test whether it's viable, and if natural explanations fail, if nothing conventional fits the data, then unconventional ideas gain credibility. There's also the anti-tail situation, which continues to evolve in puzzling ways. The sunward pointing feature that shouldn't exist according to standard models has been observed by multiple teams using different instruments. Hubble images show it clearly. Ground-based observations confirm it. This isn't artifact or misinterpretation. There's genuinely material extending toward the Sun from the nucleus, in apparent defiance of radiation pressure and solar wind that should push everything away. Various natural explanations have been proposed. Projection effects where we're seeing tail material at specific viewing angles that make it appear sunward when it's actually pointing elsewhere. Unusual dust properties where particles are large enough or have compositions that respond differently to radiation pressure. Electromagnetic effects in the ionized coma creating structures that don't follow simple dust dynamics. Each explanation is theoretically possible, but requires specific conditions that may or may not actually apply to 3I Atlas. And notably, the sunward feature has been brightening even as overall activity declines. That's backwards. As the comet recedes from the Sun, as solar heating decreases, all features should be fading together. But observations in early December showed the sunward jet maintaining or even increasing brightness, while other structures dimmed. That temporal evolution is difficult to explain naturally. It suggests that whatever is producing the sunward feature isn't responding to solar distance in the normal way, isn't driven primarily by solar heating but by some other energy source or mechanism. If the feature is exhaust from forward-facing thrusters, if 3I Atlas is actively braking to reduce velocity for potential capture at Jupiter, then maintaining or increasing brightness makes perfect sense. The propulsion system operates according to mission requirements, firing when needed regardless of solar distance. The exhaust plume would be visible as a sunward-pointing jet that doesn't fade when natural activity declines because it's not dependent on natural processes. Testing this hypothesis requires careful trajectory analysis. If the sunward jet corresponds to actual thrust, if there's measurable deceleration in the direction the jet points, that correlation would be compelling evidence. Natural outgassing jets produce forces, but those forces point in various directions determined by vent locations and rotation. The net effect is usually small and doesn't align with any single visible feature, but artificial thrust would be perfectly aligned with the exhaust plume. The emission you see would be directly connected to the force being applied, and that correlation, if confirmed, would be very difficult to explain naturally. Now let's discuss the Jupiter encounter, because this is potentially the most important test of whether 3I Atlas is natural or artificial. The object's trajectory is carrying it toward Jupiter's Hill radius, that gravitationally stable region where orbits can persist without being disrupted by the giant planet's tidal forces. Arrival at the Hill radius is projected for early 2025, just weeks or months from now, depending on exact timing. What happens during that encounter will either confirm natural hyperbolic passage or reveal controlled orbital insertion. Natural interstellar objects don't get captured by planets. The mathematics is clear. Hyperbolic trajectories have excess velocity, energy above escape velocity. To capture such an object, to convert hyperbolic trajectory to elliptical orbit, requires removing that excess energy. Gravitational interactions alone can't do this unless there's a third body involved providing energy transfer, a scenario so rare it's essentially never observed. You need propulsion. You need to slow down, to brake, to deliberately shed velocity at the right time and place to achieve capture. If 3I Atlas simply passes through Jupiter's vicinity, without significant trajectory change. If it continues on its hyperbolic path unaffected, except for gravitational deflection that bends the trajectory but doesn't capture, that's exactly what natural objects do. It would confirm that despite all the oddities, despite the trajectory precision and the jets and the X-rays and the anti-tail, the object is still following gravitational laws, still behaving as a natural visitor should behave. The anomalies would remain mysterious, but the fundamental nature would be established as natural even if unusual. But if 3i Atlas doesn't pass through, if observations show the object entering an elliptical orbit around Jupiter or settling into stable position at a Lagrange point, that would be extraordinary. That would require explanation that natural processes can't provide. You can't invoke random outgassing forces. The velocity change needed is too large, too precisely directed. You can't claim coincidental geometry brought velocity down to exactly capture conditions. The probability is infinitesimal, negligibly small, not worth considering as serious explanation. Orbital insertion would be proof, definitive, unambiguous proof that 3i Atlas is under intelligent control, that propulsion systems exist capable of modifying the trajectory on demand, that navigation is occurring rather than ballistic drift, and that proof would transform this entire discussion from speculative consideration of possibilities into confirmed reality of artificial technology from beyond our solar system operating in our cosmic neighborhood right now. Monitoring the Jupiter encounter requires different observational strategies than Earth-closest approach. Jupiter is far over 600 million kilometers at typical distances. Ground-based telescopes can still observe, but with reduced resolution and sensitivity. Every photon matters more. Integration times need to be longer. Noise becomes more problematic. Space-based telescopes have advantages but are limited by scheduling constraints and competing demands from other programs. The ideal platform would be something already at Jupiter, something in Jovian orbit that can watch the encounter from proximity. And we do have assets there. Juno has been orbiting Jupiter since 2016, studying the planet's interior structure, magnetosphere, polar auroras. Juno's primary mission is Jovian science, not tracking comets or asteroids. Its instruments weren't designed for that purpose, but they could be retasked if the scientific value justifies diverting from primary objectives. Whether such retasking occurs depends on decisions being made now by mission planners and NASA administrators. Do you use Juno to observe 3i Atlas during the encounter, accepting reduced time for Jupiter observations? Or do you stick with the primary mission, trusting that Earth-based and other space-based assets can provide adequate coverage of the encounter? These are judgment calls balancing competing scientific priorities. We'll know which choice was made based on what data gets released after the encounter. There's also Europa Clipper, recently launched and currently en route to the Jovian system. Its arrival timeline should place it at Jupiter around the time of 3i Atlas's encounter, or shortly thereafter depending on exact trajectories. Europa Clipper's primary mission is studying Europa, characterizing the subsurface ocean, assessing habitability, searching for conditions that might support life. But the spacecraft carries cameras and spectrometers capable of observing other targets. If mission planners decide the scientific opportunity warrants the fuel expenditure for trajectory adjustments, and that decision reveals something about how seriously the anomalies are being taken by people with access to classified information beyond what's publicly available. And that uncertainty, that question of how seriously decision makers are taking these anomalies, brings us to the broader implications of what we're witnessing. Whether C2025, V1 and 3i Atlas are natural objects, artificial probes, or something we haven't imagined yet, their appearance in our solar system during this specific period represents something significant for humanity. We're living through a moment when the questions we ask about our cosmic context are being tested by actual observations rather than remaining purely theoretical, and how we handle that moment, how we respond to uncertainty and mystery and the possibility of profound discovery, will shape not just our scientific understanding, but our cultural relationship with the universe. Let's start with the implications if both objects prove to be natural. If C2025 V1 is confirmed as an Oort Cloud comet, and 3i Atlas as an unusual but ultimately conventional interstellar visitor, what does that tell us? First, it confirms that interstellar objects pass through our solar system, regularly enough that detecting multiple examples within a few years is normal rather than extraordinary. The discovery rate is limited by our observation capabilities, not by the actual frequency of visits. As surveys improve, as telescopes become more sensitive and coverage becomes more comprehensive, we'll detect more interstellar visitors. That's already happening with programs like Atlas and Pan-STARRS scanning the sky continuously. Second, it tells us that interstellar objects show considerable diversity. Oumuamua was elongated and inactive. Tussis Borisov was a normal-looking comet. 3I Atlas is hyperactive with unusual geometry. This diversity mirrors what we see in solar system objects, where comets and asteroids exhibit wide ranges of properties despite forming in the same stellar system. If interstellar space contains similar diversity, if every stellar system ejects objects with varied compositions and structures, then the sample we've detected so far is just beginning to reveal the full spectrum of what's out there. Third, it validates the importance of rapid response observation. When an interstellar object is detected, you have limited time to study it before it recedes beyond effective observation range. Weeks to months typically, depending on trajectory and brightness. During that window, you need to mobilize telescopes, coordinate observations, collect as much data as possible. The infrastructure for doing this, the networks of observers and the protocols for sharing data, and the willingness to divert resources from other programs, all of this has been developed and tested through the 3 confirmed interstellar objects we've detected. Each one teaches us how to do better next time. And fourth, if the objects are natural, it means the anomalies we've observed, the trajectory precision, and the jet geometry and the X-ray emission and everything else, all of it falls within the range of natural processes even if we don't fully understand the mechanisms yet. That expands our knowledge of what's possible in cometary physics, in how ices sublimate and dust behaves, and trajectories evolve under various forces. The universe is teaching us that our models need refinement, that natural processes produce more diverse outcomes than we anticipated. That's valuable scientific progress even if it's not the revolutionary discovery that artificial technology would represent. But now consider the implications if the objects prove to be artificial, if accumulating evidence makes the technology hypothesis untenable to dismiss. The consequences cascade in multiple directions simultaneously. Scientifically, it confirms that intelligence exists beyond Earth, that technological civilizations arise in the universe, that we're not alone in developing the capacity to explore space and send missions to other stellar systems. That's the most profound discovery imaginable, answering questions that humanity has asked for millennia about our cosmic context and our significance in the universe. But it also raises immediate follow-on questions. How common is intelligence in the galaxy? Are these probes from a single civilization or from multiple sources? How long have they been visiting our solar system? Are they observing us specifically or just cataloguing stellar systems as part of a broader survey? What level of technology do they represent? Are we seeing the products of a civilization centuries ahead of us, or millions of years ahead? Each question opens new avenues of inquiry that we're not prepared to explore because we lack data, lack context, lack any framework for understanding intelligence that might be fundamentally different from human cognition. Culturally and philosophically, the impact is equally profound. Humanity's self-concept has evolved through a series of humbling discoveries. We learned Earth isn't the center of the solar system. We learned the solar system isn't the center of the galaxy. We learned the galaxy is one among billions. Each step displaced us from centrality, revealed our cosmic insignificance in spatial terms. But we maintained uniqueness in another dimension: intelligence, technology, civilization. We were unique as far as we knew, the only source of understanding and purpose in a vast unconscious universe. Confirmed artificial probes eliminates that uniqueness. We become one example among many, our technological achievements anticipated by others who likely surpassed us long ago, our existence known to observers who have been watching without revealing themselves. That's simultaneously exciting and humbling, inspiring and unsettling. It means the universe is full of meaning and purpose beyond what we create. It means we're not alone bearing the burden of consciousness. But it also means we're not special, not central to cosmic significance. Just another civilization among potentially millions that arise, develop technology, and eventually either expand beyond their origin worlds or fail and disappear. Different people will respond to this discovery differently based on their worldviews and values. Some will feel excitement, wonder, vindication that beliefs about cosmic companionship are confirmed. Others will feel anxiety, fear about intentions we can't determine and capabilities we can't match. Religious communities will grapple with theological implications, asking where extraterrestrial intelligence fits within frameworks that often place humanity at the center of creation narratives. Scientists will face the reality that our understanding of the universe, already known to be incomplete, has gaps we didn't even recognize until confronted with technology from civilizations whose physics and engineering exceed ours. Politically, the discovery creates challenges for international coordination and decision-making. Who speaks for humanity if contact becomes possible? The United Nations has protocols for this through the Committee on the Peaceful Uses of Outer Space, but those protocols assume detection of radio signals from distant stars, not physical objects in our solar system that might be watching us right now. The timescales are different, the implications are different. The need for rapid, coordinated response exceeds what international bureaucracies are designed to handle, and there's the question of disclosure. If classified assets confirm artificial origin before public data does, if intelligence agencies and military space programs know the truth weeks or months before scientists can prove it publicly, what do they do with that information? Do they disclose immediately, accepting the disruption that announcement will cause but respecting democratic principles of transparency? Or do they delay, managing information release to control panic and prevent adversaries from exploiting chaos, but violating the public's right to know about discoveries that affect all humanity? These aren't hypothetical questions anymore. If 3i Atlas is artificial, if the Jupiter encounter in early 2025 produces evidence that can't be explained naturally, these decisions will need to be made in real time by real people facing unprecedented situations with no precedent to guide them. And whatever they decide, whatever path they choose between transparency and control, between immediate disclosure and managed release, those decisions will be criticized. Some will argue they moved too fast, created unnecessary panic, destabilized systems that need stability. Others will argue they moved too slow, withheld information citizens deserved, made decisions without democratic input. There's no perfect choice. Every option has costs. The best we can hope for is that decision-makers act in good faith, that they balance competing priorities thoughtfully, that they recognize the magnitude of what's at stake and give it the serious consideration it deserves. And that requires us as citizens and observers to be prepared for various outcomes, to think through how we'd respond to confirmation of artificial origin, to avoid being paralyzed by shock if and when the moment arrives. So what should you be thinking about? What mental preparation makes sense given the possibility, however uncertain, that we might be months away from confirmed contact with extraterrestrial technology? First, recognize that your initial emotional response, whatever it is valid. Excitement, fear, wonder, anxiety, skepticism, all of these are reasonable reactions to extraordinary news. Don't judge yourself for feeling what you feel, but also don't let initial reactions determine your long-term response. Give yourself time to process, read multiple sources, think critically about claims and evidence, form considered judgments rather than reactive positions. Second, maintain epistemic humility. We don't know what artificial technology from another civilization would look like. We don't know what purposes it might serve. We don't know what intentions or ethics or values might guide its creators. Making confident claims about any of this is premature. Better to acknowledge uncertainty, to hold multiple possibilities in mind simultaneously, to wait for evidence before forming strong beliefs. The universe has surprised us repeatedly. It will likely surprise us again in ways we haven't anticipated. Third, resist tribal polarization. When confirmation comes, if it comes, there will be pressure to align with one of two camps: believers who accept the discovery enthusiastically and skeptics who resist accepting implications. But reality doesn't care about tribal affiliations. Evidence is what it is regardless of whether we want it to support particular conclusions. Try to stay in the uncomfortable middle ground where you evaluate data honestly rather than filtering it through predetermined frameworks. Fourth, demand transparency from institutions while recognizing legitimate security concerns. There's a balance between the public's right to know and the need to protect capabilities that might be compromised by disclosure. That balance is hard to find. Different people will place it at different points, but we can all agree that more transparency is better than less. The defaults should favor disclosure unless there are compelling specific reasons for secrecy, and that those reasons should be articulated and scrutinized rather than accepted uncritically. And fifth, maintain curiosity about what we might learn. If 3i Atlas and C2025 V1 are artificial, they represent data sources about technology and engineering and physics that could accelerate our own development dramatically. Even if we can't communicate with whoever sent them, even if they're just autonomous probes executing programmed instructions, without active intelligence guiding them, studying their construction and operations could reveal principles we haven't discovered. That's the optimistic view, the perspective that contact represents opportunity rather than threat, a chance to learn and grow and expand our capabilities beyond current limitations. Now let's discuss what happens with ongoing observation of both objects, because regardless of whether they're natural or artificial, the scientific work continues. For C2025 V1, tracking proceeds as the object moves through its orbit. Position measurements accumulate. The orbital solution refines. Spectroscopy will be attempted as brightness allows, though the object is faint enough that only large telescopes will achieve adequate signal-to-noise for detailed composition analysis. Photometry continues, watching for brightness variations that might indicate rotation or activity changes. The key decision point for C2025 V1 comes when sufficient data exists to determine whether the original orbit, extrapolated back before planetary perturbations, had eccentricity above or below 1. If below, it's Oort Cloud confirmed, native to our solar system, unrelated to 3i, Atlas except by timing. If above, it's genuinely interstellar, which reopens questions about connections and common origin. That determination requires months of data typically, enough observations to model planetary effects accurately and separate them from the intrinsic orbit. But there's a possibility that might accelerate conclusions. If C2025 V1 shows clear non-gravitational acceleration that can't be explained by outgassing, if the trajectory evolution indicates active propulsion, that would be strong evidence for artificial origin regardless of whether the nominal eccentricity is above or below 1. Natural Oort Cloud comets don't have engines. They don't make course corrections. They follow ballistic trajectories modified only by gravitational forces and the gentle push from asymmetric outgassing. Active navigation is a signature of technology, unambiguous in ways that other anomalies aren't. For 3i Atlas, the observation timeline is more compressed. December 19th, closest approach to Earth, provides the optimal window that's now just days away. Every major observatory with time allocated will observe. JWST, Hubble, Chandra, ground-based facilities from multiple continents, all collecting data simultaneously in different wavelengths, building a comprehensive multispectral dataset that captures the object's properties in unprecedented detail. And then the Jupiter encounter follows in early 2025, probably January or February depending on exact timing, providing the definitive test of whether orbital insertion occurs. Between these two events, between Earth closest approach and Jupiter encounter, lies a period of intense analysis. The data from December 19th will take time to process. JWST observations need calibration and spectral extraction. X-ray data requires careful background subtraction and spectral modeling. Optical spectroscopy needs line identification and abundance calculations. All of this is technical work performed by specialists who understand the instruments and the analysis techniques, and it's work that can't be rushed without sacrificing quality. So there will be a gap, a period of weeks or months, where observations have been collected but results haven't been fully analysed and published. During that gap, preliminary findings might leak. Researchers might share early results at conferences or in private communications. Rumours might circulate about what the data shows, and that creates opportunity for misinformation, for partial truths to be amplified into false certainty, for speculation to be treated as established fact. We'll need to be careful during that period, distinguishing between confirmed results published in peer-reviewed literature and unconfirmed claims that might be wrong or misinterpreted. The Jupiter encounter itself will be observable in real time as it happens. Telescopes will track 3i Atlas as it approaches Jupiter's Hill radius. Position measurements will show whether the trajectory curves into capture orbit or continues through on hyperbolic path. That's something we'll know within days of the event, not months. The observations are straightforward. Either the object gets captured or it doesn't. There's no ambiguity, no need for complex analysis. You measure where it is, you calculate where it's going, and the answer is clear. If capture occurs, If 3I Atlas enters elliptical orbit around Jupiter or settles at a Lagrange point, the response will be immediate and intense. That's the smoking gun, the observation that can't be explained naturally, that forces acknowledgement of artificial control. News will spread instantly through academic networks and social media. Within hours, everyone interested in space or astronomy or the possibility of extraterrestrial intelligence will know. And the conversation shifts fundamentally from maybe it's artificial to how do we understand what this artificial object is doing? If 3I Atlas passes through without capture, if it continues on hyperbolic trajectory as natural objects do, the interpretation becomes more complex. Does that prove natural origin? Or does it just mean the object's mission didn't include Jupiter capture, that it's continuing to some other destination beyond our solar system, that the Hill radius approach was for observation rather than orbital insertion? The absence of capture doesn't rule out artificial origin, it just fails to confirm it definitively. And we're left with the same ambiguity we have now, the same debate about whether accumulated anomalies justify the artificial hypothesis or whether natural explanations suffice. That potential for ongoing ambiguity, for the mystery to remain unresolved even after the Jupiter encounter, is something we should prepare for psychologically. We want definitive answers. We want clear resolution. But the universe doesn't owe us clarity. Reality might be messy, might present evidence that's suggestive but not conclusive, might leave us uncertain even after we've done everything we can to observe and analyze. And if that happens, we'll need to live with that uncertainty, to accept that some questions remain open, to resist the temptation toward premature closure just because uncertainty feels uncomfortable. There's also the question of what other discoveries might occur. If 3I Atlas really is part of a coordinated mission, if C2025 V1 is related, then there might be additional objects we haven't detected yet. Survey programs are continuing. Atlas and Pan-STARRS and other automated systems scan the sky every night looking for moving objects. Anything unusual, anything showing anomalous motion or unexpected properties, gets flagged for follow-up. And in the current environment of heightened attention, observers are looking more carefully, asking more questions, being more willing to investigate things that might previously have been dismissed as unremarkable. So we might see more discoveries in coming months, more objects with unusual orbits, more visitors that appear during this same period. And if that happens, if we go from 2 unusual objects to 3 or 4 or 5, the statistical argument for coincidence becomes untenable. 1 or 2 objects might be random chance. But multiple arrivals within a short window, all showing properties that stand out from normal distributions, that's a pattern. That's evidence of coordination, of planning, of intentional activity rather than random cosmic traffic. The possibility of imminent additional discoveries adds urgency to paying attention now, to following developments as they happen, rather than waiting for eventual summaries or documentaries that come out years later. Because if we are witnessing something historic, if these objects do represent first contact, or at least first confirmed detection of extraterrestrial technology, the story is unfolding in real time. We're not reading history, we're watching it happen. And that's a privilege, an opportunity to be present, for moments that future generations will study and analyze and wish they could have experienced firsthand. Now, before we close, let's address the specific question that motivated this entire exploration. Could C2025 V1 and 3I Atlas come from the same place outside our solar system? Based on current evidence, the answer is complex and conditional. If C2025 V1 proves to be Oort Cloud origin with eccentricity below 1, when planetary perturbations are properly accounted for, then no, they're not from the same external source. 3I Atlas is clearly interstellar. C2025 V1 would be solar system native. They're unrelated except by coincidental timing. If C2025 V1 proves to be genuinely interstellar with eccentricity remaining above 1, even after careful orbital analysis, then maybe they could be from the same stellar system. 2 objects ejected from the same protoplanetary disk, travelling through interstellar space on similar trajectories, arriving at our solar system within a year of each other. That's improbable but not impossible. It requires specific initial conditions and fortunate geometry, but doesn't violate physics. And if their compositions match, if spectroscopy shows similar isotopic ratios and molecular abundances, that would support common origin even though it doesn't prove it definitively. If either or both objects show unambiguous evidence of artificial origin, of active propulsion, or trajectory control that can't be explained naturally, then the question of common origin becomes a question of mission architecture rather than just orbital mechanics. Were they both sent by the same civilization, as part of the same mission or separate missions? The perpendicular orbital planes might be deliberate design, maximizing coverage of the solar system by approaching from different directions. The timing might be coordinated, scheduled arrival windows calculated to provide optimal observation coverage. We can't answer these questions definitively yet. We need more data. We need the results from December 19th observations. We need to see what happens at Jupiter. We need careful orbital analysis of C2025 V1 as more positions accumulate. We need spectroscopy comparing compositions. We need time for specialists to examine evidence carefully and build models that either fit observations with natural processes or require invoking artificial explanations because natural ones fail. But we can say that we're asking the right questions, that we're taking the observations seriously, that we're not dismissing anomalies reflexively, but examining them honestly. And that's progress. That's how science works when confronting genuine mysteries. You collect data. You propose explanations. You test them rigorously. You follow evidence even when it leads to uncomfortable conclusions. And you maintain intellectual honesty about uncertainty while working to reduce that uncertainty through better observations and more sophisticated analysis. So where does this leave us? We have two unusual objects in our solar system right now. One is clearly from beyond, the third confirmed interstellar visitor. The other might be from the Oort Cloud or might be interstellar, with current data ambiguous. Both show properties that deserve attention and careful study. Both raise questions about what's normal and what's anomalous, about what natural processes can produce, and what requires artificial explanations, and both are observable, trackable, analyzable through instruments and techniques we've developed precisely for situations like this. The next few months will be crucial. December 19th for 3i Atlas, early 2025 for the Jupiter encounter, ongoing orbital refinement for C2025 V1. Each of these represents an opportunity to learn, to gather data that might resolve uncertainties or at least constrain possibilities, and we'll be watching, along with astronomers and space agencies and everyone else who recognizes that these objects, whether natural or artificial, represent something significant for our understanding of the universe and our place in it. Stay curious. Stay critical. Question claims, but don't dismiss possibilities just because they're unfamiliar. Follow the observations as they're released. Read the papers when they're published. Think about implications, but don't rush to conclusions. And most importantly, appreciate that you're living through a time when these questions are being tested, when speculation is giving way to data, when we might be on the verge of discoveries that change everything, or might learn that the universe is strange in ways we anticipated, but not revolutionary in the ways we hoped. Either outcome has value, either teaches us something important, and regardless of which it is, the process of asking questions and seeking answers and following evidence, that process itself represents the best of what humanity can be. Curious, thoughtful, honest about uncertainty, persistent in pursuit of truth, and humble enough to recognize that the universe is under no obligation to match our expectations or satisfy our preferences, but we can study it anyway and learn what it's willing to teach those patient enough to observe carefully and brave enough to acknowledge when reality contradicts comfortable assumptions. So thank you for joining me on this exploration. Thank you for engaging with these questions and thinking through implications and maintaining the open-minded skepticism that serves us well when confronting mysteries that don't yet have clear answers. The story continues, the observations proceed, and we'll be here to discuss what they reveal, whatever that turns out to be, because that's what this is fundamentally about. Paying attention to what's happening above us, asking what it means, and sharing that journey of discovery with anyone curious enough to wonder whether we're alone or accompanied, whether these visitors are natural or artificial, whether the universe is exactly as our theories suggest or stranger than we've yet imagined, and being willing to update our beliefs when evidence demands it rather than clinging to familiar frameworks, just because they're comfortable, which is the hardest thing about honest inquiry, but also the most important because truth doesn't care about our preferences, and the universe continues doing what it does regardless of whether we understand it correctly, and our best hope for eventual understanding is to keep watching, keep measuring, keep questioning, and keep following wherever the evidence leads, even when, and especially when, it leads somewhere unexpected. That's it for today. If this satisfied your curiosity, if you found value in exploring these questions, give this video a like and share it with anyone else who's wondering about these strange visitors and what they might represent for our cosmic future.